Sorry about that. Welcome everyone. Today we have Alberto who will tell us about symplectic capacities.
Etc. Yes, thanks a lot for the invitation. And the talk is 50 minutes, 60 minutes? 60.
Yeah.
Okay, symplectic capacity. Well, of course, you all know what symplectic capacities are. Yeah, let me fix the notation. Here I'm talking about normalized symplectic capacity, and I'm just interested. Now we have this nice symplectic space Cn with coordinates j plus I by j, and the symplectic form is the standard one. And symplectic capacities are functions, let's say, from open subsets and domains. Cn to 0 plus infinity included, which are monotone. So A embeds symplectically into A prime. We have capacity of A less or equal than capacity of A prime. And there's a conformal property, the capacity of RA is R squared, so you scale as areas. And then, yeah, the important thing is now defining a normalized symplectic capacity. So the important thing is the normalization. So here we are requiring that the capacity of the ball is the unit ball in dimension in the Cn is the same as the capacity of the cylinder, okay? The Z such that Z1 1, and it's, let's say, pi. Okay, and as you all know, these symplectic capacities were introduced in Fraunhofer in the late 80s, actually. Yeah, just after Gromov.
87 at the Institute.
87, okay. So 2 years, so that was exactly 2 years after Gromov, well, after the appearance of Gromov paper on the non-squeezing theorem. Of course, the motivation was, okay, non-squeezing theorem says that you cannot squeeze this big ball into a thin cylinder. Can we also build some numerical abstractions for such things? And yeah, this is an example of such an abstraction. And of course, then, well, if you prove that a symplectic capacity exists, then you trivially get the non-squeezing theorem as a consequence. And conversely, if you know that the symplectic that non-squeezing is true, then you get two, let's say, important but difficult to compute capacities, namely the smallest possible capacity. So this is the Gromov width for ball capacity. So I denote it with C underlined. No, this is the supremum of our pi r squared, such that the ball of radius r embeds symplectically into A. And the other one is the cylindrical capacity, and denoted with C upper line. And this is, you look at the smallest cylinder in which you can symplectically embed your set. So infimum of pi r squared, such that now it's A embeds into the cylinder CR. Okay, and so these two properties are clearly true for both of them, but the important thing is if you also have no squeezing, if you know that no squeezing theorem is true, you get that these are two normalized capacities and they are the extremal ones. So another important thing is that every symplectic capacity is squeezed between those. Okay, and then I think it was already maybe if not the late 80s, at least maybe in the 90s, that the following conjecture was formulated, namely all normalized symplectic capacities coincide on convex domains. So as far as I know, this appears really stated as a conjecture. The first paper I saw it appears is a paper from Edtmair in year 2000, but I'm sure that you guys were thinking about this much before.
Yeah. Is it true that they are not true for non-convex domains?
Yes, yeah. That's yes. So of course, well, many capacities have been constructed, and then already in this in the world of star-shaped domains in R2N, it's easy to find examples where these two extremal ones are different. Okay, but then yeah, in this industry of producing capacities, at least in the good old days, people also wanted to compute things. When people introduced the new capacities, they checked what their value was on convex domains, and so for most, for many normalized symplectic capacities, it is true that the capacity of A, when this is convex, this agrees with the systole. So what do I mean by the systole? Let's say for a moment that our convex domain has a smooth boundary, and then as a hypersurface in Cn, where we also have a symplectic form, it has a characteristic, there is a characteristic foliation, and the systole is the minimal action of a closed orbit of this characteristic foliation. Okay, that's the systole. It's known since Einstein that you always have closed characteristics on convex domains. And then, for instance, when Helmut and Edtmair introduced what is now known as the Overextender capacity, they also proved that it agrees from the systole, and the same is known to be true for many other capacities. Notably, it's not known for these two, but for many it is known. So this, in a sense, gives some evidence for this conjecture, and then this conjecture became it acquired the importance when Viterbo made another conjecture about capacities on convex domains. Viterbo's conjecture is that if C, so C is again, as here, a normalized symplectic capacity, and A is a convex domain, and Viterbo's conjecture is a bound, is an upper bound for the capacity in terms of volume. Okay, capacity of A, let's say to the power n, is less or equal than n factorial volume Okay, this is really the Euclidean volume in Cn with equality, even if A is symplectomorphic to a ball. Okay, this is Viterbo's conjecture, which is also open, and it's of course related to this because this conjecture holds trivially for the ball capacity or Gromov width, and embed this ball, then your volume should better be bigger than the volume of the ball. So at least to be precise, the inequality holds for this, not characterization. And for this reason, this conjecture here, now in the recent literature, is also called strong Viterbo conjecture. Okay, just because it implies this inequality. Okay, and the Viterbo conjecture has also other consequences, for instance, another conjecture in complex geometry, but that's a different story. Okay, and then let's come to results. The theorem I want to comment on today, this is the joint with Gabriele Benedetti. Benedetti and Oliver Edtmair. So, theorem one says that so this conjecture is true for domains which are C2 close to a ball. Okay, so all normalized symplectic capacities coincide in a C2 neighborhood. Balls. Okay, so we're talking now about smooth domains. If this domain is C2 close to a ball, then the thing is true, and then this we can immediately.
You know how big that neighborhood is?
It's pretty small. Yeah, one could try to quantify it. Yeah, it's quite small. And it's a C2 neighborhood. The second theorem is that if you replace C2 closeness by C1 closeness, this is not true anymore. So there exists a one-parameter family of domains. Let's call it A lambda. Lambda is in 0, 1. These are all nice smooth domains. A lambda converges to the ball for lambda going to 0, but in C1. And for these domains, what happens is that the ball capacity of A lambda is strictly less than the system. Okay, which is less or equal than the cylindrical capacity. Well, this inequality holds just because there exists spectral. Oh no, okay. Now these are not convex domains, or for convex domain, for non-convex domain, the systole is not necessarily a capacity, but this inequality holds because you do have some capacities which are spectral, meaning they pick up the action of some closed characteristic, and then they will. This is of course smaller than those, which is smaller than this. Okay, so in that sense, this this C2 thing is optimal, and of course, C2 is also the right distance to stay convex. Okay, something which is C1 close to a ball, it just means that it's something like this. The slopes are already close to them, but you can by C1 closeness you can of course destroy convexity. Although it's probably delicate to show that these examples we build are not convex. Actually, I don't know. Yes.
If you started with something that's strictly convex and that you know both normalized capacities coincide, would you do a similar argument?
No, our argument really uses that it's close to the ball. What I'm now hoping is that one can push it probably to all domains which are invariant under there is this the S1 action on Cn, which is just given by multiplication by complex number of modulus 1.
Mm-hmm.
I believe that these methods can be pushed to those. So if you perturb one of those, then all symplectic capacities should coincide. But then just knowing that for a set they all coincide, you don't know how to use this information. This sense of symmetry is sort of rare. Yes.
Another question. So how much is all these results conjectures are true if you're in, let's say, complex projective space like CPN or something like that? Is this thing?
I know it's a different setting. What you want to use as convex subsets of. And also about the term, I don't know if there is if there are similar conjectures about I don't know, about the CPN with various symplectic forms. I don't know. Okay, more questions about
So it means
results?
in the examples you have, there cannot be an optimally squeezed ball. Because if it would be, then
Yes.
you would have equality.
Yes, if yes, whenever you have an optimally squeezed area, you would have equality. Yes, here there is no
So
optimal.
is that being used that in the argument? Is there a way to use that?
It's not used directly. The way we prove this is
I mean, so in some sense, you could imagine that the embedded is sort of so rugged in some sense because you want that if you assume you have an optimally squeezed ball, you run into difficulties and solve the symplectic geometry of that rugged set.
Yeah, these sets are actually they really look like balls. In the sense you start with the ball, you can actually do the perturbation if you want just here. You can concentrate your perturbation. Actually, it's useful to concentrate the perturbation close to one rep.
But you use the dynamics.
And you use the dynamics. Yes.
Presumably, if something would be optimally squeezed, then nearby something couldn't turn right or something.
The argument is this: you take the ball, you want to modify a bit, let's say near one Hopf orbit, near one periodic orbit, in order to reduce a bit the volume. But you want to reduce the volume in such a way not to reduce the system. And if you can do this, you take your ball, you reduce a bit the volume, but you don't touch the systole, then of course, since you have reduced the volume, a fortiori This is what we do. Exactly. And so here in particular, of course, there is no optimal squeezed. Well, no, I'm not. No, it's not clear. There could.
I think if it's optimally squeezed, then you would have a common periodic orbit.
But it's not, well, if it's symmetric, of course. If it's S1 symmetric, of course, but if it's not S1 symmetric, that's not clear. You don't have this optimal squeeze. It could touch in only a few points.
So I'm going to say, if it would.
Yeah.
So in particular, the systolic ratio of this example is higher.
Yes, the systolic ratio of this example is a bit above.
And how do you compute the Gromov width? Will it tell us later?
No. Here the Gromov width is just, this bound is just given by, since the volume, so the thing, since the systolic ratio is bigger than 1, in particular, the volume is, so the Gromov width is just bounded by the volume.
Yeah.
So it's just Banach. Yeah. Okay, so maybe something, well, maybe before I talk about proofs, so you can also wonder, of course, all these conjectures are open, why try to make more conjecture, but of course it's very natural to wonder since there's a sequence.
First genre.
Yeah, first genre. Since, so these normalized capacities actually are usually the first one of some sequences of capacities. Now, for instance, there are the so-called Eckland-Hofer capacities. This is a sequence of capacities, and there are the capacities which come out from symplectic homology. There's something called Jean Gut and Michael Hutchings. So you have nice sequences of capacities, and so the first one is usually normalized, but then you have all the other ones, and you can ask, what happens to these conjectures for other capacities? And here, actually, a theorem that we can also prove, but basically by the same method, is that many of these capacities actually share the same value on ellipsoids. If you take an ellipsoid A1n, so symplectically, by means of a linear symplectic transformation, you can always bring an ellipsoid in a nice standard form. This one. The normalization is probably to write it in this way, J1n, and here we have Cj squared divided by Aj. Less than 1. Okay, this is the standard complex ellipsoid, and I will denote by C hat K of such a guy. This is the kth element, okay, smallest element in the list, where you take all Aj and you multiply by all possible natural numbers H. Okay, so J goes from 1 to n, and H is a natural number, so it's greater than 1. Okay, so you allow repetitions and you count the kth element. This is K hat of this ellipsoid. And both the sequence, both the kth Eckland-Hofer capacity and the kth Gut-Hutchings capacity, they have this value on ellipsoid. And then you could say, okay, a capacity C is K normalized if it has this value on ellipsoid. If C of an ellipsoid is CK hat of an ellipsoid for all ellipsoids. Okay, with this language, the usual normalization would be one normalized. Actually, in this normalization, yeah, you could think, okay, you could trade cylinder. So cylinder is a limiting case of an ellipsoid. Trade cylinders with ellipsoids. Okay, and then theorem 3 is actually saying that all n normalized symplectic capacities coincide again in a simple neighborhood of a ball. So C too close to a ball. Well, the important thing is that this n is precisely this n here. Okay, it's half of the dimension of this vector space. Because instead, this is definitely not true if you take other case. So, for instance, in if you take the maybe more correct. Well, if I take, for instance, the polydisk 1,1, so this is the product of two disks, two same disks in two symplectic planes. So we know we are in R4. Actually, on polydisks, it is true that all capacities which are normalized, like the second one, they do coincide. This is easy to show. But then if you go up, if you look at the third capacity, fourth capacity, then it's not anymore true that they coincide. What you can do is, you can exactly mimicking these definitions here. You can build a C underlying K and a C overlying K just by looking at, you look at the supremum or the infimum of CK hat, such that you either embed into an ellipsoid or an ellipsoid embeds in your set. So you get a minimal and a maximal K normalized capacities. And what happens is that all these K normalized capacities, but with K3 or larger, they differ. They're not equal here. And the reason is that inside here, there is an optimal embedding, well, optimal in terms of volume. There is the ellipsoid 1, 2 has the same volume and embeds here, but then the Eckland-Hofer capacities are bigger than this. Apart from the first two, which are the same, then they start getting bigger. That's a bit okay. So if there is some generalization to higher capacity, it looks like that the nth one is somehow special, at least from we see now. Questions about this? Is it? Okay. Then maybe proofs. So proofs. So okay, here this is a dynamical construction. Really construct a dynamical system with the technology to construct these domains is actually, instead of constructing a domain, you construct a Hamiltonian diffeo, let's say, of a ball in one dimension less, of a ball in Cn-1, and then you somehow lift this dynamics to be to become you look actually the mapping torus of this thing, and then you see you embed it into this here. This is what you this is for theorem 2. For theorem 1, in theorem 1, I should also say that here, so the statement is actually a bit more precise. What is true is that if you take, so you take your convex body, which is C2 close to a ball, it will have a systole. Then, well, first of all, there exists a symplectic embedding. The symplectic diffeo is really defined on the whole Cn, which maps the ball with the systole into your convex body. And the other way around, there exists another symplectomorphism, which is again global, which maps the convex body into the cylinder with that systole. So in other words, the supremum and infimum in this case, in which the things are smooth and C2 close to the ball, are really achieved. And they are achieved by symplectomorphism, which are globally defined. That would be the complete statement here. Okay. And then, yeah, okay, so it means here you have to prove two things. You have to prove then coincidence with the cylindrical capacity on one side, which means that you have, somehow you have your convex body, so this is the ball, then you perturb it a bit, and you want one bed into a cylinder with the same, symplectic into a cylinder in the with the same width. And this part is actually not too difficult. It's a bit delicate really to reach this C2 distance. I think if somebody who was, you were in Lumini, I will also talk about this thing, but there was a C3, and there was not this example. Now at least this thing of closeness is now really somehow optimal. There is C2 and there are counterexamples. So it's a bit delicate if you really want to really do C2, but if you don't care about how far, it's really easy to understand, because you know you have this ball and then you perturb it a bit. You perturb it a bit and you look at the systole. So this orbit, closed orbit of minimal action. This systole will be very close to a systole of the ball, one of these Hopf circles. And then, since it's closed, you can, by a means of a symplectomorphism, which will be close to the density, you can put it into a plane, a complex line. Okay? Just because you have this thing which is close to a group. Well, if you want symplectomorphism, act transitively on closed curves having the same action. Action is the only thing. And in this case, you can also do it with a symplectomorphism, which will be very close to the density. And now your symplectomorphism has taken the systole, now it's planar, it's on a plane. But if it was really close to the density, it still maps this strictly convex set, because the set was close to a ball, so it was in particular strictly convex, into something which is still convex. Okay, and then you have this nice systole on a plane, and the thing is convex, so it's already physically inside the cylinder based on this thing. Okay, this, if you really want to run that argument, you have to write here a C3. If you will work a bit more with variations of this argument, going down to C2. Okay, but in a sense, the more delicate thing is the comparison with the cylinder, with the ball capacity or Gromov width. Okay, because now, now again, I have my ball, I perturb it a bit, and there will be a systole, but now I want to squeeze in a ball, and the ball will want to get out from all sides. It's not as a, before the situation was that the touching set before the perturbation was just one periodic orbit. Now the touching set of the ball with the ball is the whole thing. So it's much more delicate, this thing. Okay, and then then of course you switch a bit gears. Instead of working with domains and symplectomorphism, domains are a bit nasty thing to work on. They don't have an algebraic, you cannot add domains, subtract domains, they don't have good algebraic properties. Then first change of gears, you work with contact forms. Okay, contact forms are forms, you can add them, differentiate them, do a lot of stuff. No, and as you all know, there is a one-to-one correspondence. If I'm looking now at the 2n-1 dimensional sphere with some standard contact structure. Okay, this is okay. Let's say on R2n, we also have, I call it lambda 0, the standard primitive of the complex structure of the the symplectic structure, xj dyj minus yj xj. And this is the kernel of lambda 0 restricted to this. Okay, this is our standard type sphere. And then I call F, in this case, as 2n-1 psi standard. This is the space of all contact forms supporting this contact structure, which means eventually they're all of the form. So these are these are contact forms supporting this contact structure, which means they're nothing else but a function times this. Maybe this restriction, let me give it another name, alpha naught. Alpha naught is this standard one, and these are all things of the form f times alpha naught, where f is some smooth positive function. Okay, then I want to work here because this is a nice thing. And as you know, there is a one-to-one correspondence between these things and, let's say, star-shaped domains. Whereby star-shaped, stretching a bit the word star-shaped. Star-shaped actually here means it's a smooth domain in Cn, neighborhood of the origin, and the boundary is a hypersurface which is transverse to the radial direction. That's what we mean by star-shaped. And there is a one correspondence now, which is just given my star, in this direction, my star-shaped domain like this. I can see it as want to do this thing, I really see at the set of points of the form R U, where U is in the sphere, and R is between 0 and, if you want to really to have this, is f of u, f squared. Square or no, square root. I always mix that up. I think it's square. Okay, so what do I mean? I mean, so of course, by any positive function, smooth positive function, for instance, this I can model all my sets. And the thing is, if the set is defined like this, then if I consider just here the radial, the map which from the sphere maps there just radial, the radial projection. So here I can just have this domain, and I can use my domain W, and I can look at lambda 0 restricted to the boundary of W. And then if I pull back this is a contact form. If I pull it back to the sphere, what I get is exactly this. Okay, so I forget about now domains, and we look at the contact forms. And so what we actually proved is a theorem about convex forms. Say this theorem, and then let me also say other. Yeah, where that theorem then leads us. Maybe, yeah. Before maybe stating this theorem, I should also remind you, this is what we were saying with Helmut 20 minutes ago, but so the strong Viterbo conjecture is trivially true for domains which are S1 symmetric, right? Symmetric with respect to the action on Cn given by multiplication complex numbers of modulus 1. Not just because I have my symmetric space, symmetric convex thing, I take the biggest ball which is contained in it, and now by the S1 symmetry, it will touch. If it touches, it will touch tangential at one point, but it actually touches at the whole S1. And okay, now we look, of course, the whole strong Viterbo conjecture would be true, but now I'm looking at the one side. Now I want to show that the ball capacity equals the systole, and here now this orbit, this touching thing is an orbit on the boundary of a ball, but the ball and the convex body are tangent there, so it's also an orbit on our convex body, and so we did find a close characteristic with this action. We're very happy. The systole is maybe even smaller in principle, but then we've proven inequality we wanted to prove. Okay, so when when a convex body is S1 symmetric, even the strong Viterbo conjecture is trivial. And now in our situation, we are perturbing an S1 symmetric thing. So we cannot hope that the perturbation will keep the symmetry, or I don't know, nobody knows. Nobody knows. But what we can hope is that, so after this perturbation, the convex, or not convex, yeah, this convex body will not be anymore S1 symmetric, but what we can hope is that when we do this process, when we take this largest ball enclosed, where it touches, this part is S1 symmetric. So that we have the symmetry in this touching set, okay? Because if we get this, we are in any case happy. We don't really need the symmetry anywhere else. We just need the symmetry in this touching set. This is the starting idea of the thing. And how do you translate this into contact forms? So this is again a theorem 4. So it's a normal form for contact form which are close to. So this actually works in general. Now I have a contact manifold M with the contact structure psi, and I take a contact form here, so F and psi, which is Zoll. By Zoll I mean the red flow defines a free S1 action. All orbits are periodic and the same action. And then the theorem says that if another contact form, alpha, is C2 close to alpha naught, then there exists a contactomorphism, actually the identity component. The contactomorphism of M psi is the identity component, which puts our alpha in a nicer thing. So phi star alpha has this form. It's a function t times a function e to the h times alpha naught. I have to tell you, of course, now I haven't said nothing. I'm just saying it's a contact homomorphism. Will map, of course, alpha into some function times alpha naught. But now these two functions, t and h, have nice properties, such that, so t is a wonderful function. T is S1 invariant. T is, so this is a infinity function on M, and it is invariant. So I mean here invariant under, so remember we have this Zoll contact form, this induces an S1 action, and I'm saying T is invariant. So if I had only T, I would be super happy. It would be exactly the same in the model, in the case of domains, these were S1 symmetric domains. Okay, this I cannot hope. I also have this disturbance, but this disturbance is not bad. H is also a smooth function, and it has the property that it vanishes, and also its differential vanishes on the critical set of T. The critical set of T consists of circle, because an S1 invariant function, so its critical set is also S1 invariant, and on all of that, H is 0, so H is not invariant, but it vanishes also with its differential there. The third property, which is actually, in a sense, a consequence of the two, once you quantify them, is that T is like now a variational principle for detecting short periodic orbits. So more precisely, so there is a one-to-one correspondence between short closed of alpha. What I mean by short Reg orbit, I'm perturbing a flow which was completely periodic, and then it's a classical result. It's proven in the paper of Banger. When you perturb such a situation, you will create a bunch of periodic orbits of period very close to this common period they have. In all the other orbits, there might be many more periodic orbits, but they will have huge period. Okay, these are the ones with period nearby, I call them the short ones. Okay, there is one and the critical set. Actually, maybe I wrote it in a funny way. What I mean is that really phi, the correspondence is phi. Phi of the critical. If I move by phi my critical set, I get exactly all the periodic orbits, all the short ones. And since from these two properties, also it follows also that the period is period equals. So the function t also gives you the period up to, well, you have to multiply by the common period of alpha naught. So it's, if you want, the systole of alpha naught, which is a funny way to write the common period of alpha naught times t. This is the correspondence. Okay, and the last but most important thing is that, okay, this function t and the function t multiplied by e to the h are different functions. This is not anymore invariant, but the important thing is that the minimum or also the maximum of t e to the h is precisely the same as the minimum or the maximum of t. Okay. But once you have this, you're done, because since this is the crucial property, the thing with the minimum. Now, because you take your contact, you have your ball, then you perturb it. This perturbation is associated to a contact form close to the Zoll contact form of the ball. And then by this theorem, you can, by means of this contactomorphism, you can move it in such a way that this function T to the EH, now this was the function which in our description of star-shaped set was measuring the distance from the origin, has the property that it has the same minimum as here, which is exactly what you wanted. You wanted to have that the touching set with the ball is achieved really on an S1 invariant thing. So the touching set will correspond to taking the minimum of this function. And this minimum of this function in general could be maybe just an isolated point. Instead, it's not an isolated point. It's really no. Okay, so this is the thing. Questions?
Yeah. So can I think of this B as like choosing a contactomorphic Zoll contact form? Like a different-
Yes, you could also think that you're moving the contact form all by a contactomorphic one. Yes, yes. And then you're referring everything
Okay.
back to that.
Can I? So one trivial way to get an invariant function out of or invariant contact form out of any contact form is like to average it, right, over
Yes,
orbits.
yes.
How is T something similar to that, or
Yeah, well.
because of this fee?
There is averaging involved, but it's more involved. No? And you cannot be too trivial because this is really a variational principle. It's not that you find periodic orbits just by averaging and then miraculously you get the thing. So the way, so this theorem, maybe then this I can also show you why is very similar. Is, if you want, is the flow version of what happens. You know, the statement that if you have a symplectomorphism which is close to the identity, then it's generated by a quasi-autonomous Hamiltonian. Right? So a Hamiltonian such that its maximum and minimum doesn't don't maximize and minimize, don't move with time. This, if you want, is the red flow equivalent of that. These are quasi-invariant contact forms. If a contact form is too close to another one, okay, it's not invariant, so it doesn't. So in this analogy, there is not this. You have autonomous Hamiltonian, which here will play the role of S1 invariant contact forms. Contact form which is not, it's close to a Zoll one. Okay, it's not autonomous, so it's not invariant, but it's quasi-invariant in this precise. The difference is that the proof of this theorem is much more difficult than the proof of the statement, the Hamiltonian statement. The Hamiltonian statement only about it. The first proof is to Gabriele and Potterovich and just use generating functions. And here this uses a theorem of Botkol on perturbing vector fields plus 3 or 4 Moser arguments to really get to that. And everything is made even more complicated because you want to really not to waste time. So it's a more delicate thing.
And what can the sum of it survives if you're not C2 close? Like if you're just convex?
What survives?
Sum of
No,
the
nothing
split. Some of
survives.
the
No, this
small.
is really, here everything breaks down. Nothing survives. I really have to, this is really a perturbative result. The starting point, this Botkol theorem is about something about perturbing vector fields. It's not even symplectic, but you are perturbing a flow which is C1 close to a periodic flow. However, so this theorem dies. However, then you can start a bit thinking. For instance, if you looked at at the Hofer metric, you also know that these quasi-autonomous Hamiltonians are relevant because these are the geodesics in the Hofer metric. Also here it looks something similar, and it's actually so. Maybe you have 5 minutes, right? Yeah, maybe in this last 5 minutes I can. So I think nothing more about the proof of this. Maybe something about metrics, because I think in my title there were also these metrics, which then at least they appear in the last 5 minutes. Which metrics I'm referring to? So if I take now 2 contact forms on the same on one contact manifold, I can define a pseudo distance, which in some sense mimics the Hofer metric, which is this. I take the infimum of max f minus min f over all f such that, so here there exists a contactomorphism, and I also want it to be an identity component, such that phi star of beta is e to the f times alpha. So in other words, you have these 2 different contact forms. By means of contactomorphism, you can of course change this conformal. So beta is some function times alpha because same contact structure. But by moving with the contactomorphism, you can change this conformal factor, and you try to do it in such a way so to minimize its oscillation. Okay, this you define, you find easily that it's a pseudometric. It's a pseudometric. Here. Okay. And then there are 2 nice things. When this infimum is actually achieved, this need not to be the case, but if it is achieved, then you really have, between alpha and beta, you really have a geodesic, a minimizing geodesic with respect to this pseudometric. Not only, but in the case when this minimum is achieved, not only you have a minimal geodesic, but you also have, so it's achieved by some function. You look at this function, you take its maximal set and minimal set, and in the maximal set and in the minimal set, you find an invariant subset of the dynamics, invariant for both flows, for the flow of alpha and beta, which is contained one in the minimal and one in the maximal. Okay? These are easy things to show. When you do have a geodesic, you have this very nice structure. So in particular, if you apply it if one of those is Zoll, so I start with my Zoll 1. If I have this nice minimizing geodesic to another one, maybe very far. If I have this minimizing geodesic, meaning that here this is achieved, then I get this function f, and I have the maximum and the minimum, and in the maximal set, I have a set which an invariant set for both, but invariant sets here are just periodic orbits. So it means I did find periodic orbits of this in the maximal set of f and also in the minimal set of f, and this immediately implies that, for instance, the systolic ratio of alpha is less or equal to the systolic ratio of alpha naught. Okay. Okay, this is if you have a geodesic. But then by using this theorem, what you can prove is that if alpha is C2 close to alpha naught, you actually have such a minimizing geodesic with respect to this pseudometric. So you can retranslate these results in the language of geodesics with respect to these pseudometrics. And of course, now the temptation is to say, by starting from the ball, you prove the Viterbo conjecture because you can reach, by minimizing geodesic, all other contact forms which come from a convex thing. But of course, we have no idea why convexity should enter in this existence statement for geodesic, but I find it a nice way to look at this. Okay, I think I already went over time. Thank you very much.
So you believe in the double conjecture?
Yes, at least dimension 4, yes. Dimension 4, yes. Dimension, who knows? No, there are many.
It's true.
Can you say how you get your theory? You said it was a similar idea. What was it? Normalized?
Of the other capacities.
Yeah, for the n normalized.
Yes, yeah. Actually, instead of using this minimum, you use the maximum now.
Mhm.
Because if you think theorem 3, what you have to prove, I have this set close to a ball, and you have what you have to show this time is a bit different. You have to show that you find a ball outside. In this case, you have to find a ball outside whose width is given by the end capacity of this set. So you have to find the ball outside exactly. And then an ellipsoid inside. Well, actually, outside it means that you have to find an ellipsoid inside and an ellipsoid outside again. But actually, what we prove is that outside we will really find a ball, and you find a ball just because you do exactly the same thing, but you look at the maximum this time. And then you find, and again, instead of find the ellipsoid inside is again easier because you have a lot of room to play with. So it's really the same proof.
But then it's not clear what happens between 1 and n.
That's also not clear exactly. I thought a bit, yeah, because of course with the examples we have in R4, there's nothing between, and in R6, I think it's not true. I think that you can find counterexamples where these. But then, you have to construct, to prove counter, at least the way I've seen now to construct counterexample is you have to construct a Morse function such that if you do a critical level, you try to find it as a min-max or a max-min, they are different. Something of this sort. One is good in finding Morse functions with your nice property, and maybe one can disprove this. But the example we have are only for k bigger than n. The true examples we have. Maybe just since I mentioned this pseudometric, another interesting question has nothing to do with systolic inequalities. Is also to understand when it becomes a metric. No, because of course it's a pseudometric just because it's invariant. As it's written, it's invariant under action of contactomorphism and also by rescaling. If you multiply alpha by a constant, it will have zero distance from itself. Okay, but then you can ask, okay, mod this operation. What's the distance between alpha and all beta, which are not really conjugate to alpha? And then sometimes this distance is nevertheless zero. Sometimes instead it's positive, and it really depends on the dynamics of alpha in a way which is for now a bit mysterious. Understood this for now only for if alpha is it comes from an ellipsoid in R4. If alpha comes from an ellipsoid in R4, then if it's a rational ellipsoid, it has positive distance from anything else. If it's irrational but with Liouville frequency, it has zero distance from other things, which is very much related to these examples that Helmut and Eliashberg, these domains which are symplectomorphic, but such as the dynamics on the boundary is not symplectomorphic, and it's basically Anosov-Katok stuff. So also nice questions related to this.
Yeah, that was our least successful paper. I think nobody read it. Maybe.
I did.
Oh, okay, congratulations.
I did the paper,
Gold medal.
and yes.
Yeah, so
Yeah.
I thought that was a
But-
sort of good direction to look at.
Yes. But I think when you wrote that paper, you didn't know Annals of Katok, probably.
No, we might have, I don't know, well, but not connected.
Because not only
So that is a paper where we construct something like conjugation.
yes, but with with
I don't know, that I don't know, but definitely not. Maybe I knew, but I didn't connect it.
Yeah.
I don't know. Or Yasha wrote the paper, it's also a possibility.
yeah, with the experience of 25 years later, one can say that an example like this you obtain exactly by looking at the Annals of Katok thing, and it was already an example, but of course, yeah.
I remember there was some works, vaguely remember, there were some works that used barcodes to measure distances of things from like when you wanna measure mod some action of a group. Like, you know what I mean? Like you have this conjugation by contactomorphisms that makes this distance difficult.
Invariant.
Yeah, but also like difficult to compute.
Yeah.
And I think there were some works that were similar in the sense that you want to measure the distance of functions up to diffeomorphisms, or is there, do you think there is like a
So
is there a chain complex that you have in mind that you think barcode could help you measure that, something like that? Because I mean, the chain complex would be invariant under the action of the contactomorphism.
And then I don't know if some of this is done because for this metric, I think you're writing this is due to Daniel Rosen and Song. Junjan, yeah, sorry. Junjan. I think the idea was actually suggested by Leonid and Yaron.
Oh, so they probably know a lot.
Jan. And there are papers, this paper by Daniel and Junjan where they looked, but they all look at the large scale geometry of this metric. Results like big metric spaces that you can embed quasi-isometrically in these things. Then it's also related to the work also Usher. There's a version of this, instead of looking at contact forms, you can look at domains. See it as a distance between domains.
Is it the same as the Banach-Mazur?
This is
the same as the Banach-Mazur.
This is the Banach-Mazur. I think the only difference in Daniel and Jung definition, they put this instead of this, and so it's a bit less invariant, but it's Banach. This is Banach-Mazur distance on contact forms.
Okay.
But for instance, I think, if I'm not wrong, so this Banach-Mazur distance on contact form, so it stays a pseudo when you quotient by count and also by dilations, it's still just a pseudometric because of Annals of Katok on contact forms, but on domains it's not clear. I think it's not known. On domains it could be a genuine metric, exactly because this counterexample of Katok by what also Helmut and Eliashberg did, they're actually the inside domain are symplectomorphic, so they're not a counterexample to that.
For domains, that's the same as this this metric that is also kind of used in the collaboration with them, where you take a domain, you embed 1 over R and then R times the domain, you put the domain in the middle.
Yeah, that's exactly this. It's exactly this. Yeah,
under that projection.
Yes, yeah. But now Yeah, but now the bijection exists, but
Yeah.
of course what doesn't exist is the bijection between the group atom on this. One thing is symplectomorphism in the inside, and one thing is contactomorphism up to the boundary. So that's why the two questions about whether this is a true measure of pseudometric are different in the two settings.
Yeah.
And in one case, the answer is no, no, no. And the other case, as far as you know, the answer is not no.
So what is the, you said it's a pseudometric after you take the quotient because of this and also per top example. So you have the irrational ellipsoid. What's the other thing?
Exactly. So the thing is this, no? Take alpha is now given by irrational ellipsoid, really with you will thing. And then as another top says that you find a sequence of contactomorphisms such that this converges actually C infinity to another one.
Right.
But where the dynamics here is completely different. For instance, it has a dense orbit, or it's even ergodic. Okay, so this means this I open because what does it? Maybe I have to tell you first this. What does it mean that?
Yeah. No, I understand.
Yeah. So yeah, it's saying that this distance is positive for every beta which is not conjugated means exactly that the orbit, I take alpha, I take the whole orbit by contactomorphism or dilation, it means that this is a C0 closed set. And sometimes it's true when it's a rational ellipse, it is a C0 closed set, but in this case, it's not even C infinity closed. So this really, you have C infinity convergence to something with a completely different dynamic. So this is not in point applied to alpha, and so but nevertheless the distance is zero because the convergence is infinity. You just needed C0 convergence to have. That's why.
Are there any examples that are not periodic that this is closed?
Not that I know, because the only thing we can really understand are these ellipses, but one could think that if you take a nose of, if you take a contact form which produces an nose of red flow, then this could be a bit rigid, no? Because if I have a sequence, no, because the thing is, you have this nose of red flow, you have you conjugate, you convert to another flow, but then, so then you have many things which pass to the limit. You know, for instance, all spectral invariant. So the new thing, the new guy will have all the same spectral invariants. Wherever spectral invariant, all spectral invariants are usually C0 continuous, so they will be the same for this other thing. And so you need something which is fully determined by its spectral invariance. And if one thinks about these questions in rigidity in dynamics, one would maybe hope that maybe in some annals of case you have this rigidity, the spectral invariant determine your system up to conjugacy. But I don't think this is proven.
Good talk.
Yeah.